If you have been watching these videos, you will realize that I like to tell stories. Well, there are more stories to tell, but at this point, we need to take a break from our historical narrative and adopt an axiomatic approach to quantum mechanics because I feel this is the more systematic way to approach the subject. But we will return to the historical narrative at later points. Um, you would also have noticed that uh, I don't, even for a lay audience, I don't necessarily um, avoid the math, uh, but so far the math has been more of historical interest, and although I have outlined the derivations, I have not necessarily gone through them in great detail. Um, but a couple of things are um, essential to an understanding of quantum mechanics, and one is probability, and the other is linear algebra. So we will approach the axiomatic treatment of quantum mechanics through these topics. In classical probability theory, the first thing to note is that simultaneous probabilities of independent events compound multiplicatively. Thus, to find the simultaneous probability of two independent, that is non-interacting events A and B, we multiply the probabilities of the two events A and B. That is, the simultaneous probability P of 1 and 2 is equal to P of 1 times P of 2. The probabilities of mutually exclusive events, however, compounds additively. Thus, to find the probability of mutually exclusive events A or B, we add the probabilities of events A and B. P of 1 or 2 is equal to P of 1 plus P of 2. It was an Italian gambler who gave us the first scientific study of probability theory. But Girolamo Cardano, also known as Hieronymus Cardanus or Jerome Cardan, was no ordinary gambler. He was also an accomplished mathematician, a reputed physician, astrologer, philosopher, and a prolific writer whose known works fill 7,000 pages, although many of his works are believed to have been lost. He was ambitious, dishonest, hot-tempered, quarrelsome, and at different times in his life either poverty-stricken and despised, or rich, influential, and admired. Born at Pavia in Italy, Cardan was the illegitimate son of Fazio Cardano, a Milan lawyer and mathematician, and Chiara Michera. In addition to his law practice, Fazio lectured on geometry at the University of Pavia and at the Piatti Foundation, and he was consulted by the likes of Leonardo da Vinci on matters of geometry. Fazio taught his son mathematics, and Girolamo started out as his father's legal assistant, but then went on to study medicine at Pavia University, earning his doctorate in medicine in 1525. But on account of his confrontational personality, he had a difficult time finding work after completing his studies. In 1525, he applied to the College of Physicians in Milan, but was not admitted due to his illegitimate birth. Upon his father's death, Cardan squandered his bequest and turned to gambling, using his understanding of probability to make a living off card games, dice, and chess. Cardan's book on games of chance, Liber de Ludo Alle, on casting the die, written in the 1560s but not published until 1663, contains the first ever exploration of the laws of probability, as well as a section on effective cheating methods. In his book, he considered the fundamental scientific principles governing the likelihood of achieving double sixes in the rolling of dice and how to divide the stakes if a game of dice is incomplete. The question Cardan asked was, what is the likelihood of achieving double sixes in the rolling of dice? Each die has 6 faces, each of which is equally likely, assuming that the dice are unloaded. Since the 6 different outcomes of a single die toss are mutually exclusive, that is, only one phase can be up at any time, their probabilities have to add up to 1, a certainty. That is, the probabilities of mutually exclusive events are additive. Thus, P of A equal to 6 is 1/6 is the probability of die A coming up a 6. Likewise, P of B equals 6 is also 1/6, that is the probability of die B coming up a 6. Then the probability of achieving double sixes is the simple product P of A equals 6 and B equals 6 is equal to P of A equal to 6 times P of B equals 6, which is 1/6 times 1/6 or 1/36. The fundamental assumption here is that the act of rolling or not rolling die A does not affect the outcome of the roll of die B. That is, the two dice are independent of each other and their probabilities compound multiplicatively. Similarly, if we ask what is the probability of obtaining a 5 and a 1 when rolling two dice, now there are two equally likely ways of achieving this result. The first possibility is that A comes up 1 and B comes up 5. The second possibility is that A comes up 5 and B comes up 1. These two are mutually exclusive. Thus, the probability of A equals 1 and B equals 5 plus the probability of A equals 5 and B equals 1 is 1/6 times 1/6 plus 1/6 times 1/6 or 1/36 plus 1/36, which is equal to 1/18. What is the probability of obtaining a head and a tail in a two-coin toss? Well, that is half times half plus half times half, which is equal to half, because you can have coin A being heads and coin B being tails, or coin A being tails and coin B being heads. The two coin tosses, whether performed simultaneously or sequentially, are independent of each other. Let us now turn to the famous double slit experiment. We shall perform this with a shotgun which sprays bullets at a screen which has two slits in it, and a screen at the back records where the bullets land up. Okay. So with slit 1 open and slit 2 closed, we get the curve P1, which is shown here. This is the most of the bullets land up around here, but a few of them hit the screen and deflect to the left or right, and so or deflect up or down, and so we get a probability of the bullets landing up on the screen as shown in P1. Similarly, with slit 2 open and slit 1 closed, the probability of the bullets landing up on the screen is given by P2. So now if we open both the slits and perform the same experiment, we find that the probability of the bullets landing up on the screen at the back is given by P1 plus P2, which is given by this curve out here. That is, the classical probabilities of mutually exclusive events compound additively. Now let us perform the same double slit experiment, but with electrons instead of bullets. So we replace our shotgun with an electron gun, and the rest of the experiment proceeds as before. Now we find, however, that with both slits open, we get an interference pattern. That is, there are bands of light and dark on the screen at the back. We assume that we have a photographic plate at the back which records the positions of the electrons. So we get light and dark fringes. That means that the probability of the electrons coming through slit 1 and of coming through slit 2 don't just add add up as they do in classical mechanics, but we get a curve, an interference pattern like this. Okay. So, performing the double slit experiment with electrons, we see that with slit 1 open, we get the probability as with slit 1 open and slit 2 closed, we find the probability is given by the red curve here. With slit 1 closed and slit 2 open, we find that the probability is given by the blue curve here. Now, waves, as we know, the probability is given by the amplitude squared. Okay, so we write the wave function as phi1 for the experiment with slit 1 open, and the wave function as phi2 for the experiment with slit 2 open. So P1 is equal to phi1 modulus squared, P2 is equal to phi2 modulus squared. This is what we get with the single slit patterns. However, with both slits open, slit 1 and slit 2 open, now we get P12, which is not equal to phi1 squared plus phi2 squared, but is equal to phi1 plus phi2 whole squared. Okay, so that is the double slit pattern. So in quantum mechanics, probabilities do not compound additively, but wave functions superpose. That means the the wave function for the double slit experiment is given by phi1 plus phi2, and the probability in the double slit experiment is given by P12 equal to modulus of phi1 plus phi2 whole square, and not modulus of phi1 square plus modulus of phi2 square. Okay. So in quantum mechanics, P1 probability of 1 and 2 is not equal to probability of 1 plus probability of 2. P of 1 and 2 is equal to P of 1 plus P of 2 plus interference terms. Now these interference terms can be either positive or negative. Okay, if they are positive, the waves interfere constructively, and if they are if the interference terms are negative, the waves interfere destructively at that point. Okay, so this is known as the superposition principle and is at the heart of quantum mechanics. Okay, so the superposition principle forms the very heart of quantum mechanics, as we will see. Okay. So, as we have already seen, in quantum mechanics, the probability is the square modulus of the wave function. That is, the probability is given by psi modulus square. Okay. Now psi can be real or complex. Okay, so psi modulus squared is equal to psi star psi, where psi star is the complex conjugate of psi. Okay. If psi is real, this just reduces to psi squared. Okay. And this probability interpretation of quantum mechanics was given by Max Born, who won the Nobel Prize for this probabilistic interpretation and for his other contributions to quantum mechanics in 1954. And we will talk about that, the history of the probabilistic interpretation later in this series. So, according to the superposition principle, psi of 1 and 2 is equal to psi of 1 plus psi of 2. That is, the wave functions superpose, okay, and not the probabilities are not additive. The wave functions superpose. Thus, the probability is given by the square modulus of the wave function. So P of 1 and 2 is equal to psi 1 plus psi 2 modulus squared, which, if we expand it out, is equal to modulus of psi 1 squared plus modulus of psi 2 squared plus twice modulus of psi 1 dot modulus of psi 2. And that the first term is equal to P1 The psi1 squared is equal, psi1 modulus squared is equal to P1, psi2 modulus squared is equal to P2. So this gives you P1 plus P2 plus the interference terms, which are twice modulus of psi1 dot modulus of psi2. Okay. This was given a geometric interpretation by David Hilbert, who, as we saw, was the professor of mathematics at Göttingen, and we now know this as Hilbert space. So this Hilbert space is an abstract infinite dimensional vector space. So each wave function is considered as a vector in an infinite dimensional space called the Hilbert space. So the wave function psi may be thought of as a vector in an abstract infinite dimensional space of functions, and this is known as the Hilbert space after David Hilbert. Okay, so if you have two wave functions, psi1 and psi2, we represent that as two vectors, and then the composite psi1 plus psi2 is given by the vector addition of psi1 and psi2. Therefore, the superposition principle is then nothing else but the law of composition of vectors. Okay, so this gives a simple geometric interpretation of the superposition principle in terms of the law of composition of vectors. So at this point we will generalize this to vectors and matrices in our familiar coordinate geometry. So a vector may be represented as a column vector in any basis. So that is, if the basis is the three-dimensional Cartesian basis with unit vectors I, j, and k along the x, y, and z directions, then and we write r is equal to ix plus jy plus kz. So then the column vector representation of the vector r is given by the coordinates along the three Cartesian axes along the three basis functions, and so these coordinates are x, y, and z. Okay. An operator that acts upon vectors in this space is then represented as a matrix. So if we have a matrix like this, then the matrix product of this matrix operating on this vector is given by x plus 2y, 3x minus y, and x minus z. Now, with the important point to note here, and this leads us directly to Heisenberg's observations and the uncertainty principle. So the important point to note here is that the matrix multiplication is non-commutative. Therefore, if we take two matrices A and B and multiply A times B, we get the product AB, which is different from the product if we take B times A. So that means AB is not equal to BA.